So, I welcome you all to this course, Performance Based Seismic Design of Structures, CE 842. This is the first introductory session in which I will introduce this course contents, and what are some of the topics which we will be covering in this session. If I just summarize the motivation or reasons behind this course, I can summarize them in three categories. First is traditional building codes, second is the rapid urbanization, and third is the seismic hazard. These are the three, you can say, headings in which I will be discussing the need for this course, and this will lead us to identify some of the topics which I will be covering in later sessions in this course. So, before I actually start, I want to refer to this very interesting movie. Kindly check that, The Towering Inferno, although it's very old, but still the reason which I am mentioning here is that the story revolves around a building, a high-rise building, which is subjected to fire. Please check that, Google that, and you will find different reviews, and then maybe you may end up in actually watching it also. The building was under fire, and the story revolves around what is actually happening when the fire is there and the evacuation is being done. So, they showed a structural engineer which was in real time working on the drawings and calculations and everything in that building while sitting in that building, and the public and all building officials were actually asking this question from him, that how much time we have until this building is going to collapse. And they actually showed that he worked out some calculations, drawings and everything, and finally he said that you have 15 to 20 minutes. So, then in that state of emergency, they actually devised a solution for that fire actually, and that solution was that there was a water tank on 2 floors above that floor which was under fire, and if we can explode that water tank, the water will actually come down and it will help in actually. The structural engineer was actually shown to do all those calculations there, and he concluded that the remaining structure will be able to handle that additional stresses which may be caused by that explosion when you actually hit that water tank. This whole scenario, that whole scene actually which they have shown, and that situation actually gives us an idea about what the public at large expect from structural engineers. Quick answers, and the questions like whether my building is safe or not under a particular loading, how much time it will give us before collapse in case of a certain disaster. These are some of the direct questions which public asks from all of us being structural engineers or structural designers. So, this is a very interesting scenario to understand what is expected from a structural engineer. In that movie, they showed that he was able to quickly calculate the remaining time of that building actually, but in real practice it is not that simple. You know that simulating a building under fire and predicting its remaining life before complete collapse is itself a very detailed job, and you may not be that certain that you can answer 15 minutes or 20 minutes, right? But that was a movie, but at least it shows that what is expected from us, right? So, the question from public is simple. Well, will my building safe? What level of for example damage I can expect for a certain level of loading? Building owners, they ask explicit questions about building performance. How much repair cost I have to pay if a certain level of an earthquake occur tomorrow? How much downtime I have to experience? And for example, will my building be able to sustain a magnitude this much earthquake or not? These are those direct or explicit questions which you always experience. You always face these questions from building owners. So, similarly, building officials, they ask a simple question that in case of any loss, who is the person responsible? So, they are interested in this question. The structural engineer can only say that I did follow the code, right. This is the only answer which you can give. Can you give the guarantee of your structure that it will perform in a certain way under certain loading? If you buy a particular electronic device, for example, mobile phone or television or anything, there is a warranty associated with that product. Building is our product, but we cannot give any warranty to its owner, being its structural designers. All we can say is what? That we followed that particular building code which was coming under the jurisdiction at a particular area, right, and I followed that. So, we cannot answer those explicit questions. Even if we try to answer, they will always be accompanied with ifs and buts. If this happens, the building is going to sustain this much damage or this much loss, for example. So, most of these questions we are unable to answer. Let us first accept this as a starting point, right. There is no warranty for the structure which we can give, and there are too many unknowns. We cannot actually give a warranty in this scenario. Public understanding and engineers' understanding of safety is different, right. And ultimately we have to hide behind these building codes. The traditional building codes which are enforced through law in a particular situation or in a particular area, right. So, as long as we follow the code, we can be sheltered by its provisions. If there is a certain loss which occur or an unexpected collapse, for example, the building the structural designer will hide behind the provisions of building code. All he have to prove is that he followed that code, right, in such a case. So, these building codes they specify requirements, they give acceptable solutions and also those solutions which may not be acceptable in certain situations. They prescribe detailed procedures, rules, limits, deflection checks, stress checks and strain checks, for example. Mostly they are all based on experience and they sometimes may not be always rational. Although there is a huge body of knowledge behind all of those provisions, but sometimes they may not be applicable, sometimes they may not be that explicit to certain special scenarios, for example. But our whole building industry relies on these building codes and standards, right. So, the spirit of a particular building code is to provide public safety and convenience, and it is an inherent assumption that if you comply to that, to the letter of the building code, you follow it as it is, then you will be actually able to meet that spirit, and that spirit is to provide public safety and convenience. So, building codes implicitly ensure public safety and convenience. They set up certain guidelines and rules, and it is assumed that if you follow those guidelines and rules, you will end up in safe building, right. So, the intention of building code is to provide safety, and that intention is actually fulfilled implicitly by following the letter of the code. So, building codes prescribe rules, regulations, they prescribe limits, procedures, and you are expected to follow them, right. So, they implicitly ensure that the performance of the building will be acceptable if its rules are followed, right. But there is no explicit check. All you have to do is believe on the letter of the code. If it says that a particular distance or a particular spacing between these two bars shouldn't be more than 4 inch, shouldn't be less than 4 inch, let us say, you have to follow that in its true letter, right. And it is expected that if you follow that, you will be ending in a safe design. So, the performance of the building is ensured implicitly and there is no explicit check. You will not be able to tell that what will happen if I don't follow a particular provision of the code, right? If it says that that much spacing should not be less than 4 times dia of the bar, you cannot explicitly check what will happen if you don't follow that, right? So all you have to do is to believe in the letter of the code, and it is the intention of the code which is that you will be able to provide the public safety and convenience. So the problem is that even if you comply with building code requirements and provisions, sometimes the building performance is not acceptable, right? So the assumption is that if you follow all these arbitrarily set limitations and rules and everything, you will end up in a good performance, good structural performance. The problem is that sometimes the structural performance is not acceptable in certain cases. So what we do? We end up in changing those rules every 3 years or 5 years in some you can say countries. All building codes, they are improved regularly, 3 years, 5 year cycle for example, and whatever is the state of the art research at that time findings, they are incorporated in those limits and rules. So that's how it works actually, that instead of explicitly checking the performance of the building, we set guidelines and rules for ourselves, and then all the engineers are expected to follow those. And the assumption behind that is that if we follow those, we will end up in good performance, good structural performance. But building code doesn't answer this question, that what will happen if the performance after complying a particular code is not acceptable or it's not desirable, right? There is no explicit check, right? So currently we have many traditional building codes. We know that in Pakistan we used to follow UBC 97, but it is now converted to IBC series of all building codes, International Building Code. And then there are Euro codes, country level national codes, for example Japanese code, Korean code, Australian, New Zealand codes, right? So different organizations, different countries, different you can say organizations have different codes which are result of their research and detailed experimentation, sometimes combination of research and all those other efforts. So those traditional building codes, they lack in certain areas. For example, they govern mostly the design of general normal low rise buildings. We know that 95% of the total building stock is low rise buildings. So they actually are intended to cover that building stock. They are not explicitly meant for high rise buildings. High rise building is a relative word, obviously. In different contexts, the word high rise is different, right? Sometimes a 20-story building is considered high rise in a particular environment or a scenario, but in most of the cases, for example in mega cities in developed world, 20-story building is considered a low to mid rise building, not a high rise building, right? So mostly they are not developed for building height greater than 50 meter tall. They are meant for conventional regular geometries. Most importantly, they are all prescriptive in nature. As I have started this discussion from this point, that building codes are prescriptive. Just like a doctor writes a special prescription, do this, 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 and you will be fine. Building codes are like that, right? They give you a direct solution, a direct equation, a direct limit or rule to follow, right? And it doesn't tell you that if you do not do that thing, what will happen, right? So you just have to rely on that prescription. So all building codes are prescriptive. The traditional building codes are prescriptive. They give you a step-by-step procedure or rules or limits to follow, right? But the modern building codes now, they start changing. They are incorporating the concepts related to performance based design, or they are now more performance oriented instead of prescriptive, right? But the traditional building codes, they are all cookbook type. You know, cookbook, it tells you mix this thing, cook for this much, and the recipe is ready. Same is the language for building codes, right? They are cookbook type, prescriptive. So they are limited to a certain number of structural systems. Currently we have a very advanced structural systems. For example, let me give you one or two examples. Tubular systems, then diagrid system, a structural system without any columns, for example. All of those innovative structural systems, building codes do not cover them, right? Their safety provisions and precautions and all rules and limits, they are not prescribed by the traditional building codes, and the reason is that they are meant primarily for low-rise buildings. So they do not cover these innovative shapes and forms and structural systems. So they do not include framing systems appropriate for high-rise construction. The building codes always prescribed elastic methods of analysis, which means that your computer model which you will be using for the purpose of structural analysis and design according to a particular building code will always be an elastic model, right? A building code will not recommend nonlinear analysis because it is meant for common engineer which can follow, you can say, its general provisions. So nonlinear analysis is advanced analysis. Not everyone can actually go into its details, and also it is time consuming, and structural designers want quick answer. So building codes always recommend linear elastic analysis, and in order to incorporate different nonlinear effects, it prescribes different empirical factors, factor for this thing, factor for that thing, right? And you know there is a list of detailed safety factors and some other factors. So it kind of gives you a direct recipe. In order to account for a particular nonlinear phenomena, you have to make a detailed nonlinear computer model and then perform a nonlinear analysis. Instead, a building code will say that apply that factor and it will take care of that thing, right? So this is the approach for traditional building codes. Uniform detailing rules for all members. Then enforce unreasonable demand distribution rules. Then do not take advantage of recent computation tools. For example, geometric nonlinearity. Currently, we know that just by having one click, the latest computing programs, they can account for geometric nonlinearity, maybe P delta effect. But building codes still are based on, for example, if you have the first order linear analysis, then how you can magnify the moment for the design of long columns, it have magnification factors and this and that. So if you take into account all those latest software which are already available for common practicing engineer, many of the rules and limits, they are not required, right? So traditional building codes are not exactly in alignment with the advancements in the latest computational tools, right? So these are all the shortcomings of traditional building codes which we mostly use and follow, which we actually use to hide behind and avoid all those explicit questions from building owners and public officials, for example, right? So this is the very first motivation for development of performance based design, that building codes ensure performance of the building implicitly and not explicitly, right? They just claim that follow us and you will be safe, just like a doctor giving you a prescription, right? So then there are certain questions which you might have thought also, I think, when you follow a particular building code in its letter. For example, different building codes differ. For example, Euro codes provide a different safety margin compared to American family of building codes, and then different individual countries, they modified those factors according to their requirements. So all building codes are different, right? But you cannot kind of inform your structure to follow a particular building code in case of an earthquake, structure will follow its own mechanics, right? It is not bound to follow a particular building code. So, if all of those building codes differ, can they all be correct? They cannot be all correct, obviously, if they differ, right? So, they all can be approximate, they all can be wrong in certain assumptions, for example. So, also we cannot instruct our structure to follow a particular building code. If we select a building code to design a particular structure, it does not mean that the structure follows the intention of that code automatically. It will follow its own mechanics. It depends on its mass, its stiffness, its damping, all that, right? Similarly, building codes change after every 3 to 5 years. What happens is that we set a rule for ourselves to follow, and we then come to know that this rule is not correct, it requires some improvement. So, we come up with a newer version of building codes, and it changes after every 3 to 5 years, depending upon which code family you are talking about. But what should we do with those structures which are already designed according to that previous code, right? Right? If we are improving our codes regularly, do we also need to improve our structures regularly? This is one question which naturally comes in mind when you think that code is what is ensuring performance, right? Similarly, codes intend for life safety, not damage limits or cost implications. The intention behind building code is life safety, right? Life safety is the performance which the code writer keeps in his mind, right? He is not concerned with the cost implications. For example, in 2011 Christchurch earthquake, this is the classical example, please check that one on internet. 2011 Christchurch earthquake in New Zealand. Most of the city was structurally safe in that earthquake, but there were huge cost implications. Businesses were stopped, and there were several cost implications. There was a significant downtime for several of the industrial buildings, commercial buildings, for example. So, most of the buildings were safe according to the intention of building codes, right? Building codes intention was life safety, and there was very less social loss, very few casualties in that particular earthquake, but the cost implications were huge. And then this was a classical example when people actually experienced that the intentions of building code are not what are always required or always desired. For example, if I am a developer, for example a real estate developer, and I have many high-rise buildings, I will not want my buildings to have downtime for few months even, right? So, I would pay more at the structural design level in order to ensure that there is no downtime after an earthquake, right? If, for example, there is a non-structural damage, it may still cost huge, you can say, economic loss. If, for example, there are only partitions which are damaged after an earthquake, or just few contents, building contents, I as a developer may not allow that loss actually. So, I am not only satisfied with life safety, I want to go beyond that. In that case, building codes are they may not help, right? Because they just have a uniform intention behind all of their provisions that they have to ensure life safety, right? So, this is also one motivation for performance based design, that you have to actually ensure that all of the requirements which we want to have or follow in a particular design have to follow. Let me give you an example of what is the difference between a prescriptive code and a performance oriented code. For example, this particular clause is taken from the very first building code. We can call this Hammurabi's code as the very first building code. Just check its time, 1792 BC. King Hammurabi was the king of ancient Babylon, and he wrote all of those provisions which are still, you can say, they can still be seen in some of the writings which are extracted from that time. So that specific provision, just check that one, it is from like 4000 years old. If a builder builds a house for someone and does not correct it properly, and the house which he builds falls in and kills its owner, then that builder shall be put to death. This is the clause 229 of what we call as the very first building code, right? Just try to understand that specific provision. For example, it doesn't say what is constructing it properly mean. It simply say if it is not properly constructed, which means that the requirement is directly given, but it is implicitly given. It doesn't define what it means by constructing properly, so it's implicitly given. And the house which he built falls in, which means the collapse performance is explicitly mentioned. If the house falls and it kills its owner, then that builder shall be put to death. So the consequence of non-performance is also mentioned there, right? So this clause, if we have it at this time, it would have been that there should be a parapet wall above each structure. It should have this much thickness, it should have this much height, it should be made of that much material with this much Fc prime and this much Fy. All of those would have been prescriptive, just like today's language of building codes. Instead, it simply tells us what is desired and what will happen if you do not follow that, right? This is a classical example of how a performance oriented building code looks like, right? It mentions what is required no matter how you actually do it, and it tells us what will happen if you do not comply, explicitly tells us, right? Unlike a building code which doesn't have an explicit verification of its design, right? Another example for this same difference from the Bible, this time also 1300 BC, very old, from this book of Deuteronomy. This is in Old Testament, and it says that in case you build a new house, you must also make a parapet for your roof, that you may not place blood guilt upon your house, because someone falling might fall from it, right? Again, it doesn't prescribe how that parapet wall should be constructed. It directly tells that this is what is required, this is the required performance, right? And this can be the result if you do not follow that requirement, performance requirement. But what current building codes will write, if they will specify the minimum height, they will specify minimum material properties, minimum thickness, for example, right? So this is a difference between what a prescriptive code is and what a performance oriented code is. Performance oriented code will directly tell you that this is something which you have to achieve, this is the performance objective, right? And then the engineer use all of his knowledge, all of his or her, you can say, expertise and resources and modeling and analysis, everything, to ensure that that performance objective is met, right? Simple. No limits, no rules, no tables to follow, no design aids, no flow charts, nothing, right? You are free to use any material, any height, any, you can say, solution which avoid for someone for falling from that roof, for example, right? So the modern codes, they define estimated hazard or appropriate hazard level for the design of buildings, or load levels, for example, prescribe limits on structural system, members, materials. They also prescribe the procedures for analysis and design. Even the rules for detailing are explicitly they are mentioned, and they provide specifications for construction and monitoring also. And we hope that if all of this, if we follow all of this, it will lead us to reduced vulnerability and safer structure, right. So, we follow it and it is assumed that we will be safe, right. An example of the modern codes, very detailed prescriptions. For example, inside diameter of bend in welded wire reinforcement for stirrups and ties shall not be less than 4 dB. Now, it does not tell you what will happen if it is more than 4 dB, right. So, it directly gives you this rule. What will happen if my inside diameter of bend in welded wire reinforcement for my stirrups is simply 3.9 dB? What will happen? It says less than, should not be less than 4 dB. What will happen if it is 3.9 dB? Will my structure collapse? Will everything will not work out, for example? It does not tell, right. So, the consequence of non-compliance is not explicitly mentioned, you just have to follow it, right. So, it has, for example, extremely detailed prescriptions and equations using seemingly arbitrary rounded limits with implicit meaning, right. So, do you really think that, for example, this number 4 dB, from where it come actually? It is actually a recommendation based on detailed research and empirical testing, for example, and all that, right. But the answer would not be like 4 dB directly from all of that research. Obviously, it will be rounded off towards the conservative side, obviously, but still it is something which is directly prescribed for you to follow. Similarly, if you check any code, this is ACI, this is some Indian code, directly numbers and you can say limits and prescriptions directly. Even detailing on the right hand side, you can see very detailed guidelines which you have to follow for detailing. This is just an example of how the building codes look like, what is their style or their language actually. In this context, I want to show you one interesting quote from Hardy Cross. He was actually the inventor of the moment distribution method, which was still being used, you can say, in recent past, before this finite element analysis have became most widely used analysis procedure. He actually wrote a very interesting piece of information about standardization. He said that as the size and complexity of projects increased, it became desirable and even necessary to set up a series of routine procedures for analysis and design. Routine procedures for analysis and design. So, it is necessary to set up a series. With these standardized formulas and specifications and methods, it became possible to use a greater number of men and men with less training to produce engineering works. So, if you standardize a particular procedure, even a person who have less knowledge about that will follow it as it is in a step by step manner and ultimately result in a safer design. This is Hardy Cross saying, right. Standardization as a check on fools and set up as an intellectual assembly line has served well in the engineering world. This is his typical phrase. Fools means that who do not know anything, and the other means that they know too much, right. So, he said that there should be a standardization which should be used as a check to quickly see that a particular analysis or design is okay or not okay, right. So, this procedure, this standardization actually it set up as an intellectual assembly line, just like a product is being made in a particular assembly line. Similarly, a certain design procedure that also can be standardized in that manner. So, anyone without having much knowledge about that can follow that assembly line and can produce safer designs. So, this is he is saying in that starting era of traditional building codes, and exactly you can see currently now we have, for example, greater number of men and men with less training currently producing safer designs, right. This is exactly which he have in mind at the start of this development of all those traditional building codes, right. So, currently you can see around yourself, right, all engineers can say is that they followed a particular building code without actually knowing what is the intention behind all those provisions. So, we have actually raised a generation of engineers which lie in that category. Engineering according to them is to understand a particular provision or to just follow that without going into detail of why we have that particular provision, right. What will happen if we do not follow that particular provision. So, it is like a intellectual assembly line which is currently running. So, we by definition nowadays the traditional structural engineers, they are trained to follow the procedures and equations and rules and to be conformists, right. On the other hand, if you look at architects, they are encouraged to dream and to be defiant, right. Architects on the other hand, there are no architectural codes which you have to follow, they are allowed to think of any shape and form, and this is a reason where we always have an argument. An architect will always come up with a shape and form which is structurally challenging, and you may have to have a kind of a negotiation with architects to make that particular form safe and stable, for example, right. So, just to give you an example, that if the question is that you want to determine the wall thickness and reinforcement of a water tank which have these dimensions, it is made of reinforced concrete and you are required to come up with the wall thickness. Most structural engineers, they will be able to do that, right. This is the type of a problem which we mostly deal with in day to day routine. But if I rephrase this question, if I say that design the most cost effective water tank to hold this much cubic meter of water, same volume, but now the question is rephrased. You have to consider the cost effectiveness also, and now you are allowed to have any shape. You just have to come up with a structure which can hold 36 cubic meter of water, right. So, most structural engineers, traditional structural engineers may not be able to handle this requirement. They will say that the structural geometry should be fixed for us first in order for us to calculate the reinforcement, right. This requires initial conceptualization of structure also, which mostly our structural engineers they lack, right. They are dependent on architects for the initial conceptualization. So, in order to fulfill this requirement, you need what we call as a structural designer. This is a difference between a structural designer and a conventional structural engineer, that a designer actually can think big, right. What if I rephrase it again, and the question is now that design the most cost effective, beautiful and amazing water tank which can hold 36 meter cube of water. So, I call it as a structural artist which can handle these kind of questions, right. So, not only performance, safety, not only cost, but also aesthetics, right. So, your target is to design something. It may not be even you can say regular water tank structure, it can be anything which can hold 36 meter cube of water, because it will serve the purpose, right. The purpose is, the requirement is to hold 36 meter cube of water. So, you have to be a structural artist actually to handle this kind of a requirement, right. So, we start with calculating the thickness of a reinforced concrete wall which can sustain the water pressure, for example, and we end up in having these requirements, right. So, conventional building codes lack in this aspect also, because if they were successful, we would have seen it currently in our current generation of traditional structural engineers, right. But mostly they are all conformist, they follow the particular provision. So, the implicit performance objective which is behind the traditional building codes is that if a minor earthquake will occur, the structure will have a minor damage, right, and a minor earthquake can occur several times during the design life of the building. Minor earthquake is a frequent earthquake, right, and obviously a severe earthquake is a rare earthquake, right, it is not that frequent. So, the intensity of an earthquake is you can say inversely proportional to how frequent it is, right. So, if a minor earthquake occur, which can occur several times during the design life, the structure should have no damage. If a moderate level earthquake occur, the structure can have some damage, but there should be no loss of life. This is the intention behind the traditional building codes. And if a very strong earthquake occur, there can be substantial damage, but the probability of collapse should be low. The structure shouldn't be catastrophically fall down, right. So, this is the implicit performance objective. Codes says that if you follow my provisions, you will get this performance, that at low level earthquake you may experience almost no damage, moderate level some damage, but no life loss, and a severe earthquake which can occur just once in the design life, the structure can have substantial damage, but it will still remain standing. But the problem is that there is no explicit verification. You cannot check this, right. When you perform a traditional code based structural design, you just have to believe on this implicit performance objective. You cannot explicitly verify that if a very severe earthquake occur, how my design is going to behave, right.